All right, ladies and gentlemen, welcome to, I believe, the 53rd day of school. And we're going to be diving into some of the nuts and bolts of integration. Go right ahead. Be my guest. All right. So, ladies and gentlemen, we are going to be doing integration by substitution today. All right. Integration by substitution is, in my opinion, one of the most powerful tools of integration that we have. It allows us to turn really ugly looking things into really simple things that we can integrate more easily. All right. And strangely, you'll find that some of the results of these integrations are things that you would never expect them to be. All right. For example, I'm going to start with some good examples here. All right, first of all, if we look at some function that I'm planning on integrating, we haven't really paid a heck of a lot of attention to this guy. All right, we've kind of been just acknowledging its presence and ubiquitously following along with always writing it in place, but not really ever giving it any thorough workup of what it means and what does it do. And today it's going to become kind of a bit more the focus of how the math is done. Because what we're going to do is I'm going to try and do a simple example with you first. All right. Okay. So we've got an indefinite integral, and we've got lots of stuff going on in there. Okay. We have, first of all, we have a product, and then we have a power, and in there we have a sum, and we've got lots of things going on there. And it might be odd to be able to say to yourself, all right, how do we do this? Like, you might say to yourself, if I had something like the chain rule, if I had something like that, like the reverse of the chain rule, then we could maybe attack this. And in fact, we do. All right. Take a second and look at that for a minute. If I wanted to take a derivative of that, what would I wind up getting? 3x squared. All right, so, and notice, what do I have? I have a 3x squared. Aha. Hold on, wait a minute. There's more. So let's try this. We're going to say u, because it's, we're talking about u. U is going to be x to the third plus 2. Yeah.
Why did you put 2 in this?
Huh? Yeah, I don't have any bounds on this guy. What do you mean? What 2?
Oh, that.
Okay, so du dx is equal to 3x squared. So far, do we all agree? Yeah? All right, awesome. Therefore, so with this, now we have a nice set of substitutions that are going to make a lot of this stuff become a lot simpler. So my integral basically becomes all right, because that's what I said u was. So now the inside of that is u. So now I've got u to the 10th, which is simple. Okay, we can integrate that in our sleep. And this 3x squared dx now becomes du. And this is no problem to integrate. Okay? So now I wind up getting 1 over 11 u to the 11th, and, well, of course, the ubiquitous plus c. So now what I can do is I can go back and resubstitute all right. So when I mentioned before that this kind of approaches an art form, this is one of those things that leads me to that statement, in that you would have to look at that and say, wait a minute, what do I have? I've got this 3x squared in there. Oh, wait, if I make this my u, I can take a derivative of it, and there it is. You know, it's like it requires a degree of problem solving that really, it's based on experience. The more you do, the more you'll see. So let's do another. So we'll be doing them for a long time. All right, now here's an important one. All right. Cosine of 5x. Now, we know that we can take an integral of a cosine. We know what is the integral of cosine? Negative sine, because the derivative of sine is cosine. Well, would it be a negative sign or a positive sign? Positive sign. The derivative of sine is cosine. The derivative of cosine is negative sine. Okay, that's where we were. So, but we've got this 5x in here, which is kind of messing us up. So one thing you can look at and say to yourself is, if I was doing the chain rule, what would I have to do here? I would have to have what in there? I mean, like, if I do this, what do you think I would let u be in this case? When you're looking at this and you're saying to yourself, okay, I've got something funny going on here. Whatever is weird to you, whatever instinctually says, I don't know what to do there, that might be where you make your substitution. Okay? When you're looking at something and it's got fangs and teeth and you don't know how to approach it because you're afraid it'll bite you, make it into u. That's a first shot strategy. Right? It is a very, very useful tool. And sometimes you have to do substitution twice. It's really even weirder. Yeah, goofy stuff. All right, now, this is my du, is a 5 dx. Well, I don't have a 5 in there, do I? No, I don't. I have to make a 5. What was your question?
I was going to say, is it possible to do it without substitution?
Not easily. No, and this is the technique you want to use. All right, so since we don't have a 5 in there, I mean, if I had a 5 in there, I could rock and roll, and I could do my substitutions, and the game would be over in a heartbeat. But I don't have one. So what I want to do is I want to insert one artificially. Hey. Okay. Okay, everyone was looking at their clocks there for a second.
Oh my god.
Oh, yeah.
Yeah, betting is closed. I'm sorry. All right. So anyway, I am recording this, guys. All right. So the thing is that I don't have a 5, and I want a 5. Because if I can put a 5 in there, if I could artificially insert one, then I could proceed. So what I'm going to do is I'm going to do the only thing I really have. I can multiply by 1. You see, that I haven't done anything wrong. All I've done is insert a 5. I've put one in there. Now, we're going to follow that back down. And a function that is being integrated, you can think about a integration as a linear operator. Okay, and we've talked about linear operators, where you can pull a constant out, right? Okay, so leaving in only the part that I wanted. Sure. Who is this? And you see, now I can do my substitution. Yeah, it's a slick little tool. It really gets the job done. So now what I have, and I'm kind of going into some long drawn out detail here, but in order to show the point. And the integral of cosine is sine. And I can resubstitute. And you can always check your work. Oh, I just made that mistake. Whoops, excuse me. Sorry, I don't know what I was thinking there. Because one of the things that we've talked about is that integration and differentiation are inverses of each other. Okay? And when you think about an operator is anything that takes in a number, spins it around, spits another number out. Take a square root. Square root is an operator. Give it a number, feed a number into the square root animal, choose it up, spit something else out. Okay? And and the inverse operator to the square root is the square. I feed that thing back to a square. It plays with it, spits something out. And they cancel each other out in terms of one operator and another operator being inverses of each other. So I would be remiss in calling this a class on calculus and not introduce a very important feature, which is called the fundamental theorem of calculus, part 2. Yeah. So if I take the derivative of an integral, I get the function back. Nothing too fantastic or funny. And I should probably be a little bit more careful about my notation here. the well, okay. You know what? For this moment, I'm gonna keep it because usually I use the capital F to say this. You see, like if I were to if I integrate the lowercase f, it gives me the capital F. Does that fly? Okay.
Basically, it's like F.
Yeah. Whereas if I take the derivative of lowercase f, I get f prime. Okay. You could kind of think about it that way. All right. So let's keep up with this. I want to give you some more examples. Ooh. Yeah. So, what makes this guy funny? Hmm? Mm-hmm. So, what am I going to let my u be? So I just kind of like skipped a step there, but I think we all can follow, right? I just took the derivative with respect to u. No, sorry, the derivative of u with respect to x gives me this beast. Now I don't have my 3. What am I going to do? And what's the integral of e to the u or e to the x? No, I didn't. So there is my 3. So 3 dx gives me du. I pull the 1/3 out and make my substitutions. Ever play with Legos when you were a kid? Do you remember the instructions?
Dang, you're cool.
The instructions of Lego problems are fantastic because they don't have words. It's picture, 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 picture. Yeah, you have to subtract the 2 images in order to figure out what happens between step to step. So what you're basically doing is you're doing that mental image subtraction. Same thing is going on here. To go from here to there, what did I have to do? Make my substitutions, pull my 1/3 out. Now, we all remember that the derivative of e to the x is e to the x. Right? It's its own derivative. So it's safe to say that this just becomes what is with my smartboard today? The best hall pass ever. Yeah, it is. Best hall pass ever. No.
It's under that.
Next. So you try this one. I guess. Yeah, sure. Try that one. What's that? It's not cosine squared. It's cosine of x. X squared, yeah.
What does it do without substitution?
Not really.
How would you do this? Like, I really don't understand how you're getting like the 1/2 and stuff like that.
Okay, let's go back into it. So I really need a 2x, but I don't have a 2x, right? I only have an x. So what I need is to insert a 2 artificially so that I can get the full expression. Okay? So I'm going to put in a 2. So now I've got the 2x that I need. So I commute. Yeah?
Why is the 1/2 I would still want it.
Well, I have a 2 and a 1/2 right here. So the 2 came over to become part of him, and the 1/2 I don't need. He's just coming out to outside. But he's there to maintain equality, because if I multiply by 2, I have to multiply by 1/2 also in order. Otherwise, I'm just saying, hey, become 2 times bigger. It's like, you're not tall enough. Here, multiply yourself by 2. It's like, hey, you need to lose weight, multiply by 1/2. There we go. Right? That would be great, wouldn't it? Yeah. So now my substitutions become this. And so I'm substituting x squared for u and 2x dx for du.
How does du become?
You see, I'm integrating with respect to u. And the integral of cosine is just sine.
Yeah, I understand that part. But how does du become?
It doesn't. The plus c is always going to be there when you're doing indefinite integration. The du is telling me, take an integral with respect to u. Just like I would be taking an integral with respect to x. So this is now, we are integrating by looking at a different variable. Okay? When you say, with respect to something, it means that you're looking at it in that context. And here, we're integrating in the context of looking at x. So what I'm going to do to make my life a little bit easier here is think about it in terms of u. Okay?
But how does that cancel out the dx?
It doesn't cancel it out. It substitutes for it.
Oh,
Right. Because I know that 2x dx is equal to du.
oh yeah, that makes sense.
Cosine x squared, right? Yes.
Okay. Now, this is one of those integrals that appears on your formula sheets. Okay? And it's not, there's nothing really going on in here. Okay? But I want to be able to take the integral by myself without saying, oh, because, the math gods came down from the mountain and handed us this integral table. It doesn't work like that. Yeah, I mean, the Prometheus of math comes down and hands integration over to the puny humans. Doesn't quite work. So what I'm going to do is I'm going to play with this guy just a little bit. Now, looks like you and I are in the running for a couple of minutes. So let's look at this for a second, because this one's kind of weird. We have sine and cosine. Now, sine and cosine are integrals and derivatives of each other, right? Derivative of sine is cosine. Integral of cosine is sine. So we might be able to look at this and think to ourselves, wait a minute, what's going on? Okay, let's pay attention to this example for a moment, please. Thank you. Do we see anything in here that is a derivative of another guy? Who is a derivative of who? We have, well, the derivative of sine is cosine, and the derivative of cosine is negative sine. Yes? So who do you want to be the u? Who shall I substitute for? Who should be the u? Who votes cosine? Who votes sine? Okay. Now here's what will happen if we pick the wrong thing. If we chose this, my problem now is that I have a cosine in the numerator and a dx in, I have both of my terms, cosine and dx, are in my numerator, and unfortunately I have this, which is not in the right place, is it? I would like to simplify the thing that is complicated. So when you're looking at what is u, go at the thing that is complicated. The term in here that is more complicated than the other is the 1 over cosine. That should be the first place to look for a substitution.
Good morning. Please pardon this interruption. All students going on the field trip to the Museum of Natural History in D.C. with Ms. Bruce and Mr. Pat should report to the first floor cafeteria at this time. All students on the field trip, please report to the first floor cafeteria. Thank you and have a good morning.
He's probably here all the time.
No, he's not. I looked. Oh, excuse me. And now, which is a shadow away from what I do have. I'm going to multiply by, well, I'm going to multiply by 1, but it's still going to be, I mean, all I can ever do is multiply by 1. But 1 comes in various forms, right? And in this case, the form of my 1 is going to be -1 over -1. So doing all of my substitutions, he is not here yet.
Will he be?
We're taking bets on when he's actually going to show up.
Does he really show up?
Yeah, well, if he shows up, I'll give it to him, but I highly doubt it. Yeah,
Thank you.
sure.
For the IB meeting,
Yeah.
you want to cross the state?
Now, what is the integral of 1 over u? What thing, when I take a derivative of it, gives me 1 over u? Yes. And we need to put absolute value bars in there, because remember, I can't take the natural log of a negative thing. Poor little u.
Oh, that's an L. Oh. This is first.
Reminds me of 100.
Now, here's where a little bit of magic comes into play. Yeah. It's been substituted to u. No, u was cosine. We tried it with u. We tried it with sine, and it didn't fly. So here's where a little bit of mathemagic comes into play. Remember, this is a -1, right? Which, as far as a logarithm is concerned, becomes an exponent, right? Right? And now, I can do my substitutions. Logarithms are one of the things that I think students generally avoid, which is a shame because they are a beautiful topic by themselves. And if you recall your integral tables, you'll see that the integral of tangent is the natural log of the absolute value of x, which is odd, but that's why. You guys should, my recommendation is to keep that formula sheet handy, if you haven't already. The formula sheet that's on the Fusion page. It's a bit of a beast, but that formula sheet, this guy should try to be in your notebook, binder, whatever. Okay. How about this? Why don't we hit the boards? It has been a while. It's been too long. right. And since Colneat's, Colneat's still up. Hunter's out. So it's just me and Colneat now.
I think we voted, so you're the winner. Because Colleen put it at 7:42, and then later.
Oh, changed his mind? Oh, well, all right. Sorry, dude. All right. This episode of the Ronco Show has been brought to you by Substitution and Harold.